Welcome to our first colloquia talk of the DRP program of this summer. We have a very special guest today to kick off our talk series. We have Gönenç Onay from Galatasaray University. He's an assistant professor of mathematics at the Galatasaray University. Previously, he graduated from University of Grenoble and completed his master's in theoretical computer science, and afterwards did PhD in mathematical logic and algebra in Paris. He has held research and teaching position in Paris, Istanbul, and Münster as teaching research assistant, assistant professor, and postdoc, respectively, having different titles through the years. And since 2020, he has been working on topics related to machine learning, bridging pure mathematics with computational applications, and collaborating with various research institutions on interdisciplinary projects on seismology, if I'm saying correctly, archaeology, yes, and health domains. So we have a very interesting talk today for us, I believe. The title in the page was Inversion Problems in Seismology. Now we have a longer format. It's good to see. It would be informative for everyone, I guess. Unveiling Earth's Secrets, Inverse Problems in Seismology. So I'm going to hand over to Gönenç. So stage is yours.
Thank you very much. And yes, I am, as in the presentation, I am not so new to machine learning, but I am very new on this domain of seismology. I am very interested in seismology since my childhood, but learning its maths, I mean, this talk, maybe it should better be considered as a student talk because I am still learning a lot. It is not my PhD domain. So this, in fact, in this slides, there are two works. First was with Ayberk Zeytin and Çağrı Diner and with Yusuf Sezer Çar, the first part of the work. And the second part is with again Çağrı and Ayberk, but we have also Shafak from TED University and unfortunately not Yusuf for the second part. So it's all together, but they are related, as you will see. So in fact, I prepared two slides. I mean, two PDF slides. One is this is the short version. I will first go through it. I mean, there are 14 slides, and then because the other one has been a bit dense, so I just try to shorten it, and then I will go into the details with the second one. Okay, so let's start. So the question is difficult. It's an inverse problem, so we just see the effects, a representation of what happened in the Earth, and we try to, it's the inverse problem, we try to understand what happened. So where the earthquake did occur, how did the fault rupture? So for example, when you go to websites like Kandili websites, you see some numbers for coordinates of the earthquake place, but these are all estimation. These are the potential resolution of some differential equations, and there are lots of mistakes there. Okay, there are lots of approximation, and sometimes they are even completely false. There is no earthquake at that place, for example. There is no earthquake at all, but there are another thing which triggered a single that we thought that it was an earthquake. So there are a huge area for research. Okay, there are problems. They are theoretical problem. They are modelization problem, and they are computational problem. Okay, and believe me, what shocked me a bit when I began to interested in this topic. So the method they are currently used worldwide are really very old methods. So it is prone to error. This is the first problem. And the second problem is the prediction problem. So in the future, if we will have an earthquake or not, this is completely different, and that I won't talk about this problem. To predict earthquake is very difficult. Why? Because in the data meaning, because we need the data to get our data from the previous earthquake. And if you want to predict an earthquake bigger than the magnitude of 6, for example, we should have data of the earthquake, previous earthquake of that magnitude or bigger, let's say, to simplify. But this is a very rare event, okay? So even if you can construct a machine learning application, so basically it is statistic, or I mean, to learn from the training dynamics to predict something. But even if you say there will never happen an earthquake in Istanbul, it will be successful more than 99%, because in 99% of the for example, in 10 years, if you look back to 10 years in days, it didn't happen an earthquake bigger than 6, but suddenly it happens. So this is a very difficult problem. Okay. So I will try to very briefly explain classical mathematics and the modern AI approach for solving inverse problems. So we are not about predicting. This was the only short paragraph that I want to say. We are try to understand where the earthquake happened and how the fault rupture, what is the fault rupture? So I will try to define this more precisely. But the second is also related to prediction, because if you understand how the fault has been ruptured, the shear structure of it, so shear in Turkish, maybe there are lots of Turks, is the kayma, and how then we can infer how the transfer is processing the stress transfer. So in which other fault probably the stress is interacting. So if we had an earthquake in Tekirdağ, and we want to know if now the stress is on the Princess Islands or not. Okay. So we have two problems. So I will talk about inverse problem, but there is also, so one should know about forward problem. So we have a earthquake model. I mean, this can be an differential equations and some parameter of these equations. So we want to get the observation. So for example, given earthquake location and mechanism, predict what will happen in seismogram. So seismogram receives some waveform. It's like time series, like sinusoidal time series. So we want to we may want to predict this. Okay, the inverse problem is what I will talk about. Is the observation. I want to understand the model parameters which triggers this observation. Okay. So inverse problems are difficult. It is so-called ill-posed. So there are multiple possibilities that can produce the same data. This is fit to the same data. Okay. In seismology, an earthquake, so an earthquake creates two types of waves. So these P waves, it is the first waves which are emitted during a rupture. So it is the first which arrives that we feel, and it is not dangerous. The second waves are slower, and this is the destructive waves. Okay. So what are the measures that we have? We have the observation time at a station, and in seismogram we have the full waveform. So these are very big data. So for one earthquake, it can be like 20 gigabytes or like that. Okay. So from these arrival times and station localization, we want to get the local earthquake depth, for example. And we have also frequently the earth structure, what we call the velocity model. So it's a model of the earth of an area, for example, in Marmara. It's also difficult. This is the result of seismologic research. So it basically says you how the waves propagate in which in a section. Okay, it's like a you can imagine the light. If you remember the Fermat principle of the light, depending on the density of the medium, the propagation of light has different slope according to the structure. So we have a guess resulting from the real research, physical research of the Earth structure. Okay, it's a velocity model. It's also, we make it mathematical. We can mathematically describe it. Okay. So the first problem is to find the location. So these are the coordinates, and T0 is the initial time that we don't know. We only know the observation of the arrival time. Okay, but we know the velocity model. Okay, we assume that we know the velocity models. These are the geologician has provided. Okay, and it is not perfect. There are several velocity models. Okay. So that the time that we observe is approximated. We approximate via a model. Okay, a model is just a modelization. So basically, it is T0 that we want to find, the coordinate of the hypocenter, and a time travel model. Okay, so generally basic model. I will then expose this mathematical formulation, one of the mathematical formulation in, I think they are in the other slide, but for now it's just a mathematical function. Okay. And then from arbitrary location and original time, once this is calculated, so just random parameters, we can calculate this expected time, and we just compute the misfit. So between the time observed and the time calculated. Okay. And then if we pose the problem like that, the only thing that we want to do is to minimize this distance, the sum of this distance. So the big N is the number of the station. More station we have more chance to optimize the minimize the misfit error. Okay. So this is a classical optimization problem. And we can, this is, if you want to, if the people from machine learning can recognize that this is the least square error. Okay. And for example, the one of the most used methods is the linear method. So basically you do a Taylor approximation for this function, and then you try to convert to local minima just by looking to if the gradient is 0. Okay, so this is, for example, the main interface of the candidate, the solution that you see, it is computed in that way. Okay, it's very basic. So the problem with this, so as you know, this function has lots of local minima, and when you stuck in a local minima, you are not at the optimal state. Okay, so your prediction is probably it is not certain. There is an uncertainty. Okay. Okay, so there are probabilistic and nonlinear methods. So we make an assumption. So this is basically because of if we have sufficiently station and the data, we may assume, thanks to the basically big numbers theorem, so the convergence of the random variables independently distributed, identically independently distributed variables, we can reformulate our problem as a distribution for problem. So we want to estimate, so the best location of the earthquake, so location is sample. We can assume it is sampled from a distribution. It is distributed like a Gaussian. Okay, and so we want to find the area is also like in machine learning, like it's like a maximum likelihood principle in machine learning. We want to find the we want to reduce the uncertainty to find which maximize the probability of this location. Okay, but this is computationally intensive, and we can have multiple solution, etc. Okay, so okay, there is a basic algorithm, Metropolis algorithm. So we randomly start from a location, and this, in fact, I always say location, but it also encode is a 4-parameter variable, so it's also encode to t0, the original time. Okay, so we want to propose each step. We want to improve our location in a probabilistic way. Okay, so we can compute its sigma because we assume that it is distributed via a normal distribution, and we can we have the previous one, so we accept the new probability. So we are generating a probability distribution in that way. Okay. So instead of one point, we are generated a cloud in location. Okay. So the second problem of this talk, as I said, is the inverse problem. It's the how the fault rupture. Okay, for this, we have a basic object which is called moment tensor, which in fact tell us how the rupture is created. I will explain where it comes. Okay, it's a 3x3 matrix for now. It's a symmetric because we assume that locally in infinitesimal place in the fault there is no rotation. Okay, so basically this mxy is the one is the force, so one x is the force projection on, say, x coordinates. Y is the y coordinate of the fault normal. Okay, so if there is no rotation, if we assume angular preservation law, whatever it means, but there is a physical that I want to motivate it. There is a physical reason that it is symmetric. This we can summarize the force generating the rupture in that way. Okay. But we don't know how the fault rupture has happened. So we need the full waveforms, so the full data, not just arrival time, to infer this M. So if it is important, if we know M, then for example, we can make guess. So how the stress is probably transferred to other faults. Okay. Okay, what is the central role of this moment tensor? So when we convolve this moment tensor with the gradient of the green function, so maybe you heard in other problems the green function, is the solution of a certain differential equation. Then we get the displacement at the seismogram. So displacement is which generates, so from the waveform we know the displacement. So displacement, and we can measure displacement. Okay, so displacement is known. Okay. So, but computing this green function numerically is super expensive. Okay, maybe I stop here if there are some questions. So there will be other slides which is a bit more mathematically heavy, but I mean, I just want to expose for now the key notion and what we are doing. Are there any questions? Can I go on? Okay. So traditionally, we solve numerically the PDA, which is computationally expensive. And the new approach is to learn this green function as an operator via a neural network. So training will be happy, but when we have a good model, then the inference will be rapid. Okay. So the neural operator is the operator learning. So we will learn a function. Okay. So from a velocity model, we want to learn this function G, which maps velocity model to a wave field. Okay. So we can try to learn the green function. We can do direct moment tensor inversion. I mean, we can try to do, these are very new works. There are some works in the literature, but they're quite new. And we want to also, we may want to full joint inversion. Okay, we can from only seismogram, not only the moment tensor, but the source location. Okay. So these are much more speed than fast than the classical methods. Okay. So this is also, of course, matter for the Istanbul. It's a complex 3D structure which is not really understood, and we need a characterization. So as far as I am not seismologist, but when I talk with people in Kandili, in fact, they don't believe for now that what we say in the television, so we don't really know in which direction, for example, the stress is transferred. Okay. It will go in the west or in the east, we don't know. So neural operators, it increases speed, it also increase the accuracy because there are also, we can also create synthetic data, and we have some range on the uncertainty. Okay. Okay, so to summarize, we have linearized inversion, grid search, probabilistic method, sampling method for the location, and for the full moment tensor estimation, we can use hopefully neural operators and physically informed network. And we can hopefully reduce the time for this. So this was the first general overview. I mean, I maybe missed something in the chat about the sigma. So this sigma is not the same sigma. Maybe this is the mistake. Okay. This sigma is the standard deviation, and this sigma is the probability distribution. I'm sorry for this typo. Okay. So are there any questions until now?
First, maybe we can thank to you and for the talk, and then we can take the questions. So thank you, and I will just stop the recording.
No, the talk is not finished. This was a short version, so I will.
Okay.
If you permit
sorry.
me, I can go with the details of.
Sorry.
I mean, because the whole thing is, for me, is complicated. There are lots of notation, and it is also difficult. So applied mathematician, I am from pure mathematician, use a lot of terminology to say the same thing, and also in this machine learning world. So I just prepared how to say a summary version of the talk, and then I can quickly expose what I want is best. If you ask me a question, then I will pass to other slides to show you possibly, hopefully, the answers there. So if I this was the short version, and the long version. is here. Okay. This is much more detailed version. So you know now possibly what is hypocenter location problem and the moment tensor inversion, and in this long version I can answer more to your question maybe. So this is the epicenter, and this is the wave propagation, and this is the Earth structure, the velocity model. Okay. So the two waves that we have seen is the P waves and the S waves. There are also surface waves, but these are much more complex. I don't know. They said me this is much more complex, and we don't, for now, we don't care of them. So we have the real machine seismometers. Okay. Maybe you have seen in TV. Okay. Okay. So seismometers, just to have the precise arrival time. Okay. So we have the forward problem, and we want to, in the forward problem, we want to predict observable outcome. But we have the so it's like a predicting earthquake, but we want to attack inverse problem. So from observation, we want to understand the cause and what happened really. Okay. So this is ill post, as I said, and computationally heavy. Okay. So this is the misfit function that we have seen. And this is just a linear model by Taylor expansion. Okay. So this is very sensitive to velocity model, for example. Okay. This is what we solved. So we can assume the density distribution of this location is like Gaussian, and it is the conditional probability given the observed data. Okay, if you know what is conditional, if you remember what is conditional distribution. So we generate a probability distribution of the possible location. So we can create a grid and search on it. This is the expensive way. And we can also do some sampling methods. So so the MCMC algorithm is the high probability, is to give the high probability regions, is to through the random walk. It's a construction of a Markov chain. And this is a very nice algorithm, because if you know, maybe this is you start a random walk, and with some threshold, you stop. So in the previous slide, it was this selection of the acceptance criterion. But for example, I don't know if exactly they are doing the same thing now, but the first big success of Google search algorithm this how was it called? Is this graph algorithm? Whatever, it exactly uses this approach. I mean, it's a random walk, so it's estimate the probability of leaving a site following a link or not, and it's stabilized. It converts to a fixed point, which enables them to attribute a rate. So maybe you don't know, but before, I remember in 90s, the first search engines were producing result in alphabetic orders. Okay. And this changed a lot with Google algorithm, but it's not exactly the same, but this random walk approach is very interesting. So so we are exploring the entire solution space. Okay. Okay, it's a bit more less simplified version, but this is the same thing. Okay. Okay. So basically, another implementation detail. So we only need the quotient, and this is somehow good for computation. So there's another one which is called Oct-Tree method. It's the importance sampling. And this is by dividing the grid into more important space. Okay. And this is, so the MCMC create a point clouds of the distribution, but the main difference is that we have the direct probability density distribution. Okay. So in the second problem that I talked before, so we have this famous moment tensor. It's a symmetric. So the symmetry arises from the conversation of angular momentum principle. Okay. So we assume there is no rotation. Okay. But it can, of course it is. So, but this is just a simplification, but it is locally in infinitesimal area, there is no angular moment. There is no torque. Okay. So we have 6 parameters to guess. Okay. So the MEG component is the force in G direction acting on the plane whose normal is I direction. Okay. System. So this tensor, it gives us the fault orientation and scalar seismic moment. Okay. So the main thing is this representation theorem, which relates to find the moment tensor. It is enough to estimate the green function. Okay. this is the expanding form of the previous equation. So the green function is, they are both unknown. So this, okay, this also the moment tensor, it depends on time, but it is, there is also a simplification. We suppose we approximate, already we made an approximation. We say that this is a constant matrix times a univariate function, okay? It's a source time function. So there are lots of approximation in this issue, okay? Okay, if we infer from the seismograms moment tensor, then we can also compute synthetic seismograms. So which means the displacement quantity, and we can also use and evaluate and compare them. Okay. But to initiate a machine learning approach, okay, maybe I have to just say what is a data, okay? So what is an observable data? Is just we think that it's a distribution, okay? It's a realization of, it's a joint distribution. It's a realization of some random variables. So we have numerical x and y's, so a data, and we think that our observation is have been sampled from a distribution that we don't know, but we want to guess. Okay. So the seismogram data is just sampling from a distribution. Okay. So we want to infer the prediction parameters. Okay, so theta is probably a set of parameters, a tuple of parameters. So a short crash, one slide neural network. So a neural network for us, for this talk, is just a composition of affine map. So the linear map plus a constant vector, and their compositions after at each after component wise another, there's a very bad notation, always sigma, an activation function. Okay, it's just you take, so forget the bias. It's a almost composition of linear function, but when you, before you compose, for each component wise, for each coordinate, you apply some nonlinear activation function, which is, for example, sigmoid function, or a sample ReLU function, which is maximum of the x and 0, and or tangent function. So you take your vector, and in each coordinate, before you apply the next linear application, linear transformation, just you transform, you activate your coordinate of the vector with some function. So basically, for example, if you think a function, a piecewise linear function from R to R, you can represent this as a composition of linear function and before composing, you apply this ReLU. So when you cut off the negative parts, just you create a piecewise linear function. Okay. In fact, a ReLU network, it is known as a theorem that it is nothing but in high dimensional piecewise linear function, but piecewise linear in the sense of bigger dimensions. Okay, and so these are family of functions. Also, let's take ReLU networks. So like the approximation theorem by polynomials. So every sufficiently smooth function can be approximated by a piecewise linear function. So by a ReLU network. Okay, in several variables also. Okay, so when we model a problem as input output problem on a finite domain, and we assume that it is given by a generating function from a bigger from the full space plus a noise. This is typically the assumption of the machine learning. So we can, if we have enough data, we can approximate via a neural network this core generating function which generates the data distribution. Okay, this is a very short summary. Okay, so in practice, how we do it? So we are trying to learn the one good piecewise linear function, for example, a ReLU network. So we said this means that we want to learn this linear transformation, which means that we want to learn the coefficient of their matrix representations. So we start with arbitrary coefficients, almost arbitrary, and by gradient descent like algorithm, we try to optimize the best parameters of these matrices to fit to try to estimate this generating function which generates our data. Okay. So we have the seismogram data. So we want to learn the green function, for example, or moment tensor. We can formalize in this way. Okay. So it is easy if we know the Green's function. So to know the Green's function is hard. And with traditional methods, it takes a lot of time. Okay. And it is sensitive to velocity model. And it is when we go to upper dimensions, it's really becoming much more harder. Okay. So the idea is to learn this operator. Okay, it is no more a fixed data, but we want to learn a function. So basically, we want to know kind of infinitely many correspondence. Okay. So that what I talk about the neural network was MLPs is maps finite dimensional vectors to finite dimensional vectors. So neural operator, we want to learn an operator is basically an infinite dimensional function space. We want to learn a function which maps functions. Okay. This is the one key distinction that we have to address. So of course, computers are finite. So one should make this learning in a finite time and in a finite data. Okay. So one ingredient that one can use is to apply a Fourier transform and to learn the Fourier coefficient. Okay, when you can very roughly you want to learn a function, but if a Fourier basis, I mean, there is a basis. Okay, it's infinite, but you can stop at some point, and instead of learning function, you can just learn the Fourier coefficient. Okay. Okay, there are some advantages to learn Fourier functions.
Hi, Gönenç. Maybe we can wrap up in 10 minutes. It's been 1 hour, but it's also up to you if you need more time.
Okay, I can finish in 5 minutes. So these are,
Okay.
I want to say that it's complicated. That's why I make this shortened version. But it is very interesting mathematically. Okay, we want to learn map function, which are the solution of differential equations via machine learning, and the methods exist, but they are not. Maybe I will come to there are other methods. So motivate. And the most ambitious one is to learn everything from just observed seismograms. Okay. Okay, maybe I will finish with these 3 slides. So our main goal was to develop and evaluate neural operators to accelerate or replace traditional methods for seismic inverse problem. So one of these is, so we want to in fact compute some solution of the differential equations, in particular green function. So we want to learn moment tensor inversion because it's capture all the rupture characteristic. And we want to also do end-to-end joint source inversion. Okay. So we will pay a cost. The cost is just to train complex machine learning models, but then we can then rapidly infer from this model. If we can develop this kind of model from the known earthquakes or Marmara region, then we can quickly answer and possibly give better answer for the for the stress evaluation. There are also some limitations. Okay, we don't aim much generalization, so our model won't work, of course, in another area. But one real limitation is the interpretability of this huge model. It appears everywhere, so we don't understand why ChatGPT or Gemini output some answer and not other, because these are very big models. Okay. And I think that's all from me for now. And I am open to questions, of course.
Thank you so much for the talk.